Okay, so we're almost at the end of the course. I would like to introduce one last topic, which is ensemble learning. So this is an important topic. We're going to see that it's a special paradigm for learning, where instead of producing a single hypothesis based on a single algorithm, we can essentially combine multiple algorithms and multiple hypotheses to obtain better results. Okay, so we're going to have, in fact, 2 lectures on ensemble learning. For today, I'm going to talk about bagging and boosting. The motivation or the intuition behind this is that so far in the course we've seen many techniques. I've listed some of those that we talked about. There's, in fact, many more techniques out there. And then when you face a problem, an important question that often arises is simply which technique should you use and how do you know which one is going to perform best? And unfortunately, there's no good answer to this. In general, it's really a process of trial and error. So we know from the theory that some techniques are supposed to perform best in some situations, but then as you try these techniques on some problems, often, the theory doesn't quite follow in practice. I mean, some of you guys are experiencing this firsthand with some of the questions on the assignment where we know that some techniques are supposed to perform better, but then you observe results that are different, that are sometimes worse, right? So this can happen. And then so in practice, the question remains, what technique should we use? Often it's a question of trying out and seeing which one actually performs best. But then you might wonder, well, if I'm going to try all of these techniques, is there a way I could combine them? Could I get something even better by combining these techniques? Okay, so in practice, what happens is that different techniques, they yield different hypotheses, and none of those hypotheses are perfect. So when you try different techniques, often you're going to realize that one technique gives you a hypothesis that is good for a certain type of data, and then another technique gives you a different hypothesis that is better for a different type of data. And then perhaps in the data that you need to be able to handle, you have both of those types. So in other words, you don't have a perfect hypothesis. You don't have something that just works best all of the time. And now you'd like to combine those. So the question is, can we combine several imperfect hypotheses into a better hypothesis? And it turns out that the answer is yes. Okay, so here, let's make some analogies. So when it comes to ensemble learning, it is similar to some of the things that we do as a society very often. So for instance, we have elections to combine voters' choices to pick a good candidate. And we also have committees that combine experts' opinions to make better decisions. So here, we can think of the algorithms as essentially being voters for, let's say, a prediction or a classification, and then we can combine them together. So here, part of the reason why this can be attractive is that very often an individual can make some mistakes, but then it's less frequent or less likely that the majority will make mistakes. At least that's the principle that we follow when we have an election. So there are different candidates, and then obviously each person has his or her preferences. But an interesting question is what's best for society in general. And even when somebody tries to think of society as opposed to just their own preferences, they might not necessarily make the best choice. But then if we ask the population in general, then most of the time you end up with an outcome that is going to be more robust. Although we can all think of situations where despite a full election process, there have been cases in history where you can question whether the elected candidate was really the best one, right? But sometimes this is more something after the fact, and then generally speaking, a democracy with an election has this benefit that you can obtain some choices that tend to be more robust because it's rare that the majority of the people are going to be fooled or are going to make wrong choices in comparison to a single individual. Okay, so that's for the first case. Now the second case with committees, so even if we put aside election and society, in many organizations here at the university, in fact, there's lots of committees. In fact, most of the decisions are made by committees of professors, of staff, and so on. And then in companies as well, there will be committees who will bring together different expertise. So, for instance, you might have a data engineer with a software developer, with a business person, and so on, who will come together and then discuss what might be the best approach to a problem. And the idea is that they bring different expertise, they bring different points of view, and then they can arrive at a better solution this way. So here, in the same way, we might have different algorithms that are better suited for different types of data. And now, if you bring them together, you might be able to obtain a better solution overall. Okay, so as a concrete example, let's say that we consider perceptrons. These were classifiers that we saw that produce a linear separator. They're not the only type of linear separator, right? So we saw that mixtures of Gaussians can also give us linear separators and also support vector machines, right? So there's lots of classifiers that produce linear separators. And then we saw that an important question is, how can we generalize these linear separators to obtain nonlinear boundaries, right? So it turns out that through ensemble learning, we can also achieve that, where if you have some classifiers that produce some hypotheses that are limited in some way, but now if you combine several of them, you can obtain a richer class of separators. So for instance, if we consider perceptron, these are linear separators, and now we take an ensemble of perceptrons. In other words, we have a set of linear separators, then we can end up with a polytope. Right, so here, this is an example where I've got data from one class, the plus class, and then there's another class that surrounds it. These are all the minuses. And here, you see I could come up with a linear separator at the bottom, on the side here, and on the side here. And if I take the intersection of all of those, right, then I can isolate the plus class versus the minuses. And this gives me now a polytope. Right, so okay, it's a nonlinear separator, perhaps with discontinuities here. Okay, it still has some linear pieces, but still, if you have enough of those, then you can approximate some fairly complex decision boundaries. And in any case, the point here is not to come up with just an alternative solution to how we can generalize linear separators, but it's just to illustrate that if we combine several imperfect hypotheses, it is possible to obtain a hypothesis that is richer and potentially better, right? Because now we end up into a richer space of hypotheses, and as a result, we can represent separators that could not be represented before. Okay, so in general here, ensemble learning refers to this idea that we're going to have a method to select and combine an ensemble of hypotheses into hopefully a better hypothesis. Okay, so it's not always going to be better, but we're going to see that with the right type of algorithm, we can, generally speaking, obtain better results. Okay, any questions regarding this so far? Okay, very good. All right, so let's talk about our first technique. It's called bagging. It's inspired by the idea of voting. So here, let's say that we have a bag of hypotheses, or if you prefer, an ensemble of hypotheses. These hypotheses might be produced by different algorithms. We're going to see later on how we can obtain them. But let's say for now that we have different hypotheses. Now, if we want to make a classification based on different hypotheses, then a simple way could just be to get each hypothesis to make a prediction and then simply return the class that has that is the most popular among those predictions. In other words, the majority class. Right? So for some data instance x, then we get each hypothesis to effectively cast a vote for a class, and then the class that gets the most vote is the one that we could return as our prediction. Okay? Any questions regarding this? Good? Okay. So now, if we consider classification with an ensemble in this way, what's interesting is to look at what happens when we take an ensemble of several hypotheses, like let's say 5 hypotheses. Then in order for the majority to be wrong, what it means is that in the case of 5, I would need at least 3 hypotheses to be wrong. So here you see the larger is my ensemble, then to get the majority to be wrong, I will need many hypotheses to make a mistake. And then under the right type of assumptions, then we can show that this is unlikely. Okay, so let's consider some specific assumptions. So here, let's say that we have hypotheses denoted by hi, and they make some error with a probability p. So each one of them makes an error with probability p, and then those hypotheses are going to be independent. In other words, their probability of making some error is also independent, and then the type of error they might make is independent too. So if they are independent, then you see the fact that one of them makes a mistake will not necessarily mean that the others are going to make mistakes, and then when we take the majority, right, it will be more robust. Now we can verify this mathematically. So if we look at the majority voting, when we have n hypotheses, then we can compute what is the probability that k hypotheses make an error according to this equation, this expression. Right, so this here says that out of n hypotheses, I'm going to have k of them that make an error with probability p, and then the remaining n minus k will compute the correct class with probability 1 minus p. Okay, so this is from combinatorics, right? So we've got n choose k, and then so this looks at all possible subsets of k, and now each one of them will make an error with probability p, and otherwise will be correct with probability 1 minus p. Okay, so this is for k hypotheses. Now if we want the majority of the hypotheses to be wrong, then it means that we need to consider all the k's that are at least n over 2. Right? So if I've got n hypotheses in total, I guess half of them would be n over 2, and then for the majority, I need k to be greater than n over 2. So I'm going to sum all these expressions for k greater than n over 2. Okay, so now what does that mean precisely in practice? So if we take an example, like n equals 5, and let's say that each hypothesis makes an error with probability 10%, then according to this formula, the probability that an error would be made by the majority would be less than 1%. So here, I leave it up to you as an exercise. You can plug in the numbers. Okay, so here you see we've got n is equal to 5, k would be equal to 3, 4, and 5, and now p would be 10%, 1 minus p would be 90%. So if you compute this, overall, this will be less than 1%. So this is beautiful because you see we took some hypotheses that make mistakes 10% of the time, and then we combine them, just 5 of them, it's not a large number, just 5 of them, and now for the majority to be wrong, that at least 3 of them would be wrong, the error, the probability of error goes down to less than 1%. So that's a nice boost of accuracy, right, just by doing this type of pooling. Any questions regarding this? Okay, very good. All right, now the problem in practice is that the assumptions that we just talked about don't hold in general, right? So the hypotheses are rarely going to be completely independent, and those hypotheses, their probability of making a mistake is generally not going to be the same. We're typically going to have some hypotheses that are better and some hypotheses that are worse. Okay, so what can we do with this? So a simple approach could be to just take a weighted majority vote. Okay, so earlier we said we're going to take the majority vote and essentially get every hypothesis to make a prediction, pool that together, and count the votes, right? But now if we use a weighted majority vote, we can handle some of these things here. In particular, if we design the weights carefully, it might be possible to decrease the weight of correlated hypotheses. So if I have two algorithms that produce essentially the same hypothesis, then I don't want these two hypotheses to have the same vote. They're really the same, so I want perhaps to decrease them so that they just count as one hypothesis. So this is an extreme example where we would have twice the same hypothesis. In practice, you will often have hypotheses that are similar, so they're going to be correlated, and it's not so much that we can aggregate them, but still maybe we can decrease their weight, and this will take into account the correlation. So with the right set of weights, we can counter correlations. The other thing we can do with weights is that if we have some hypotheses that are better than others, then we can just give a higher weight to the better hypotheses, right? So it's a bit like you see in a committee. Let's say that a bunch of doctors are trying to make a diagnosis for a disease, and let's say that it's a disease related to skin. Let's say we've got a skin doctor, but then there's a physician, and then maybe there's a cardiologist, and maybe a bunch of other doctors. Then naturally you would think that the skin doctor would be a better expert, and maybe you want to give more weight to his advice as compared to the other doctors, right? So here in the same way, we might have algorithms that produce different hypotheses. Some hypotheses are going to be better, stronger than others, and then we might as well just give them more weights. This will help to improve the accuracy overall. Okay, so to achieve this, there is a popular framework known as boosting. And what it does is that it will compute a weighted majority vote. And the way it operates in terms of obtaining hypotheses is that it will use a Bayes learner, a Bayes learning technique that produces classifiers. And then this Bayes learner, it can be a weak learner. It can be essentially a not very good learning technique. And then by pooling a lot of its resulting hypotheses, we're going to obtain a higher accuracy, and effectively we can boost this weak learner. Okay, so when this was first proposed many years ago, this was remarkable because there was a general belief that you see algorithms that produce some hypotheses that are not very good are just not good, and we should just move on and try to design better algorithms. But what this boosting framework made us realize is that even those bad algorithms or those weak algorithms, well, if we wrap them inside a boosting technique, we might be able to essentially combine several of their hypotheses to improve the overall accuracy and compensate for their weakness. And in fact, we'll see in a moment that when I see a weak learner, it just has to be something that produces hypotheses that are slightly better than random. As long as they do better than random, we'll be able to boost them and obtain better results. Okay, so the way we're going to do this in practice will be simply by reweighting our training set. So we're going to have a base learner that takes a data set, produces a hypothesis, and then after that we're going to perturb the training set by essentially changing the weights of the data instances, and then as a result it will produce a different hypothesis. And here the intuition is that if we have some instances that are misclassified by one hypothesis, then perhaps what we can do is increase their weight, make them more important, so that the next time around, then the algorithm has a better chance of producing a hypothesis that will classify those instances correctly. Okay, so this is a little bit like you see when you're practicing in a sport, and maybe there are some moves that you're having trouble with, right? If you practice more on the moves that you're having trouble with, then you'll get better at doing those over time, right? So here's this idea that these data instances that we're having a hard time classifying, if we simply increase their weight, then we make them more important, and then there's a better chance that we're going to obtain a good accuracy. Okay, does this make sense? Any questions? Yeah?
Conceptually, is this like reinforcement learning in some way that if something is not going in the right way, you're trying to, I don't know, increase the weights and make it go the right way? Like conceptually, is it
that's an interesting thought. So usually we don't associate boosting with reinforcement learning, but I see your point that I guess reinforcement learning, you would essentially reinforce I guess good behaviors and then punish bad behaviors, and in that sense drive the learning. So at least at a high level, yeah, there's some of that going on here, but we're going to see in a moment details for a specific algorithm to do that, and it'll be completely different from reinforcement learning. Yeah. Any other questions? Okay. All right, so in terms of having a weighted training set, the idea is that we're going to use learning algorithms that can work with a weighted training set, and it turns out that in fact pretty much all supervised learning techniques can be adjusted to work with a weighted training set. So if we have weights that correspond to integers, then we could in fact simply take data instances and duplicate them to correspond to the integer weight. Okay, so this would be the simplest way of dealing with weighted data sets. But now if we have instead weights that are real numbers, positive real numbers, then we cannot just duplicate an instance to correspond to its weight. Instead, what we can do is simply change the loss function of the algorithm to have a larger penalty whenever the weight is high, and then a smaller penalty whenever the weight is small. Right? So here, for instance, when we talked about squared loss, right? So if you have different data instances and you would like the squared loss to be smaller for some data points than others by increasing their weight, then you could measure, or you could, instead of adding the squared loss of all the data points and measuring mean squared error, you could use a weighted mean squared error by essentially taking a weighted combination of the squared loss of every data point. So in general, we can work with weighted data sets in this fashion simply by changing the objective and introducing a weight for every data point. Right? So normally when we do optimization, we have a loss function, some objective, and this objective typically allows us to compute something for every data point. So we measure a loss for every data point, but now we simply multiply that loss by the weight of that data point, and that gives us automatically a way of taking into account weights. Okay, so that's what we're going to do. So we're going to learn with a weighted training set, and here in supervised learning, so we're going to minimize the training error, and we can simply bias the algorithm to learn correctly instances with high weights. Okay, so the idea that we're going to follow into our boosting framework is that whenever an instance is misclassified by a hypothesis, we're going to increase its weight so that the next hypothesis that we produce is more likely to classify it correctly. Right? So here, what we're going to see in a moment is that we can do boosting by running an algorithm on a data set. It gives us a hypothesis. Now we can check which data point it misclassified. Those data points, we can increase their weights and then rerun the algorithm. And as a result, it will produce a different hypothesis that is more likely to get those data points correctly because the weight was increased. Okay, so here's in more detail the boosting framework. So what we're going to do is to set all the instance weights. So all of our data points are going to have weights Wx that are equal, let's say, set to 1. So we're starting with just uniform weights. Then we're going to have a loop where we repeatedly learn a hypothesis hi from the data set with the corresponding weights. Okay, so this is our learning algorithm. It's going to be a base learner that works with weighted data sets. So this could be a perceptron, a support vector machine, a neural network, a decision tree. It could be any algorithm that we've discussed, right, that could be used here to produce a hypothesis. Then after this, we're going to check which instances are misclassified by the algorithm, and then we're going to increase the weights of those misclassified instances. All right, so I've got a data set. I train an algorithm to produce a hypothesis, and let's say that it gets 80% accuracy, so there's 20% of the instances that it misclassified. So for those 20% of the instances, I'm going to increase their weights so that then the next time I run the algorithm, it is more likely to get those right. Okay, so we're going to do this repeatedly. And at every step, we're going to get a different hypothesis. And in the end, we'll simply take an ensemble hypothesis to be the weighted majority of the hypothesis that we generated, where here we're going to have a weight, Wi, that is proportional to the accuracy of hi. So, okay, in this framework, there are two types of weights. There are the weights for the data points, and then there are the weights for the hypotheses. So at the beginning, we have weights that are uniform for the data points. We use that to learn a hypothesis. Then we change the weights of the data points. Whenever they get misclassified, we increase the weights, right? But then at the end, once we've collected all of those hypotheses, then we can measure how good they are based on their accuracy, right? And then we can use this accuracy to determine a weight. So we're going to use a weight, Wi, that's proportional to the accuracy of each hypothesis hi, and then take a weighted majority of those hypotheses. So the idea is that the better or the more accurate is a hypothesis, then the higher is going to be the weight. Yes?
So when you say the weight of the data point, does that mean, for example, let's say we have binary data that are labels, do we just multiply the 1 by like 1,000?
So, okay, yeah, if we have data points, and then we're doing classification, binary classification, and now we have a weight associated with each data point, then what we would multiply this weight by is not so much just the label, but we would multiply that by the loss function. So here, if we're doing classification, and let's say by minimizing negative log likelihood, then we would simply multiply the weight by the negative log likelihood. Yeah?
Sorry, don't we need to decrease the weight of the correctly classified points? Because
Oh, okay, yeah, so that's a good point. So I guess, yeah, we're increasing the weights of the things that are misclassified. Now, in reality, this will have the effect that it is implicitly decreasing the weights as well of the correctly classified ones, because it's really the relative magnitude of the weights that matter. So, in fact, depending on how this framework is implemented, in some algorithms what happens is that it's the misclassified weights that are increased, in others it's the correctly classified weights that are decreased, and then often after that there's a normalization step that just normalizes all the weights to sum up to 1.
so in this framework we just increase, and then at the end we need to renormalize everything again.
So actually the renormalization step is not even necessary. So you see, the algorithm is trying to minimize loss overall, right? So now once you've increased the weights of some instances, then I guess it will increase the loss. Now if the algorithm doesn't want to pay a higher price because the loss just got increased in this way, then it will automatically try to classify those correctly and maybe incur a loss instead for those points that have a lower weight. So even if we haven't normalized, this will happen naturally. Yeah?
That's great. Another question. Could we use, so let's say we had a bunch of data and some data is like really understanding. Could we use something like using framework framework to like initially just to make sure that those underrepresented sample data are so like, let's say I have a huge
Okay, so if I understand well, so you've got data, but then there's some data that is underrepresented, and then you would like to essentially increase the weights of this underrepresented data so that we have a better chance of classifying that correctly.
Yeah, would that be about it?
Yes, so you could do that. Now, okay, here what you're describing though is a different situation where it's just that I guess you have a data set where perhaps you don't have enough examples of a certain type of data in your training set, and you know that in practice when you're going to do the classification, perhaps you would have more of this type of data, right? And then ideally you want your training set to follow the same distribution as your test set, right? And then if they don't, then you might need to perturb the distribution. You could do this through weights. So that would be a way of doing that, but typically we would not use boosting for that reason. But we would use a similar mechanism of increasing or decreasing some weights, yes. Yeah. Yeah.
By a sufficient number of hypotheses, does that mean until the label is a hypothesis that we get from our model?
Not necessarily. So I guess when I say sufficient is it really means here that you would get a large number to a point where computationally it just becomes too onerous to generate more. Okay. So if you get a perfect hypothesis on your training set, we're going to see an example of that in a moment. It does not necessarily mean that you're done and you can just use that. It will generally be better if you combine that perfect hypothesis with many other imperfect hypotheses just to prevent overfitting. Because if you have a perfect hypothesis, this is only with respect to the training set, and then it doesn't mean that it's going to perform necessarily well with respect to the test set. So here we're going to give it a high weight because it's perfect, but we'll still take into account all these other imperfect hypotheses with smaller weights, and still overall it will tend to generalize better. Yeah?
So we'll give it a high weight since it's perfect, but we increase the weights on this classification. So,
Oh, okay. So here, let's be careful. There are weights for data points and weights for hypotheses. So when I said increase the weights for misclassification, you see these are the weights of the data points. But then at the very end, when we take our weighted majority, now we create weights for each hypothesis. And now the weights are proportional to the accuracy of that hypothesis. Yeah?
Just to clarify, the first set of weights, like the weights of the data, is just a way to increase the penalty of the misclassification. It's just
Yes. Yeah. Okay, so let's look at a picture to better understand how this algorithm works. And this is a picture that illustrates a simple scenario where we generate multiple hypotheses and then take a weighted majority vote. Okay, so in this picture, I've got green squares that correspond to data points. Okay, so let's say that I've got a very small data set, just 4 data points. And here the size of those squares is essentially proportional to the weight of each data point. So at the beginning, I start with uniform weights, so they're all equally important. Okay, so I feed this to my base learner. It produces a hypothesis. And here, just for the sake of an example, let's say that my base learner is a decision tree algorithm. So we haven't covered this in this course, but if you take the AI course, decision trees are typically covered in that course. And it's just another type of algorithm that produces a classifier. Okay, so if you prefer, this doesn't have to be a decision tree. It could be a neural network. It could be a support vector machine. It could be anything you want. Okay? The point is that it produces a hypothesis. And now this hypothesis, we could inspect it and measure its accuracy by verifying which one of the data points does it classify correctly. So here I'm going to denote by a check mark the fact that this data point is classified correctly by H1. And then a cross when this data point is misclassified by H1, and so on. Okay, so this hypothesis is not perfect. Out of 4 data points, it misclassified 2 of them. So now what I'm going to do is increase the weights. So in the next round, you see my squares become rectangles, where now suddenly you see this data point becomes larger, this one becomes larger, and then in this picture I'm renormalizing my weights. So overall you can see that this one got smaller and this one got smaller because they were correctly classified. Okay? So now I have a weighted data set. I feed this to my same learner, my same base learner, and then because the training set is different, then it will likely produce a different hypothesis. So let's say that it produces one that this time gets the first 3 examples correctly, but not the last one. So then in the next round, we increase the weight of this last data point, and then we obtain a new hypothesis H3. And let's say this one now misclassifies the 2nd and the 4th data point. So we do yet another round. And let's say in the 4th round, now we have data points with the following weights, and then we produce a hypothesis that in this case, this is just for the sake of this example, perfectly classifies the data points. So here, it's tempting to say that because it perfectly classifies everything, that we could just stop here and then use it. In fact, we will stop here simply because if it perfectly classifies everything, now when it comes to changing the weights, I've got nothing to change, right? Everything is perfectly classified. So at some level here, the algorithm cannot keep on going, so it will stop here. But when it stops here, it doesn't mean that we're going to use this hypothesis alone. What we're going to do is compute a weighted combination of these 4 hypotheses. And now the weights are going to be proportional to how good these hypotheses are. So like you see, this last hypothesis is perfect. It gets 100% accuracy. So I give it a larger weight. And here the size of my little decision tree just reflects the weight of that hypothesis. The third one had a 50% accuracy, so it has a smaller weight. Same thing for the first one. And then the second one had a, let's say, 75% accuracy. So you see it's in between. So now I'm going to take a weighted combination of all these hypotheses and then use that ensemble to make my prediction. And we do this despite the fact that we have a perfect hypothesis, simply because, again, if we want to prevent overfitting, it is generally better to combine multiple hypotheses, because there is a risk that this hypothesis here is really just fitting some noise. Right? So it's beautiful because it fits our data perfectly. We got 100% training accuracy, but that doesn't mean that we have good testing accuracy. So we combine it with the other ones. Okay, any questions regarding this picture? Yeah?
Sorry. Is it possible in practice that we have perfect classifier because we are using deep learners, right? So most probably none of them must be perfect.
Okay, yeah, good point. So yeah, if we're using deep learning and you make your neural network very large, fairly complex, it is generally possible to have perfect accuracy on the training set on the first hypothesis, and then we wouldn't be able to keep on going,
yeah,
right?
But the point is that each of these hypotheses must be a deep learner, right?
Yeah.
So deep learner, can they be perfect?
Okay, if you've got a perfect learner, then I guess it doesn't need to be boosted. Now, when we say perfect learner, I guess what you probably mean here is something that get 100% accuracy in a training set, which is not necessarily perfect on a test set. We know from deep learning that we can overfit the data tremendously. For instance, some researchers have done some experiments where they can take some image data sets like MNIST or CFAR10 and then in fact just perturb the labels, essentially reassign the labels at random, and then train a deep learning technique with convolutional neural nets and so on that are fairly expressive, and then you can still get 100% accuracy on the training set with random labels, right? So that just shows that you can get very complex hypotheses that can fit well maybe any type of data. Okay, so in this framework, yeah, you would not use a deep neural network like this. In fact, the paradigm here, the thinking here is that because we're going to generate multiple hypotheses, what you want to do is to use a base learner that is simple and quick. So deep learning is not simple and quick. Okay, so deep learning, in fact, would not be used in conjunction with ensemble learning unless the final accuracy is still far from perfect. So I guess it still gets used. Like if you look at some of the results in early competitions with for ImageNet, there were ensembles of neural networks that were used, but then they were not really reaching the peak performance yet. Okay. All right. Any other questions? Yes.
So when you've got these hypotheses and then you merge them, this means that you then retrain this new hypothesis, or you just use the weights that you have learned before?
Oh, okay. So when I create hypothesis H, effectively I do not explicitly create a hypothesis. What I'm really doing is that think of this as some sort of implicit hypothesis that corresponds to taking the weighted majority votes of those explicit hypotheses. Yeah.
There's no need to retrain it.
Yeah, so no, there's no retraining here. So we get each hypothesis, and then we simply compute a weight that's proportional, and that's it. Okay, so here's in more detail a specific algorithm known as AdaBoost that really made boosting popular many years ago. So this algorithm has two sets of weights, W and Z. I'm going to use W for the data points, and I'm going to use Z for the hypotheses. So it starts by assigning uniform weights to the data instances, and then it goes through a loop where at every step it will have a base learner that takes a data set with some weights and produces a hypothesis. Then after this, it's going to evaluate evaluate the quality of that hypothesis by measuring its error rate. So for every data point that is misclassified, we're going to add to the sum of errors the weight of that data point. Okay? And then after this, we go back, and then in this case, for every data point that is correctly classified, they're going to reduce the weight by multiplying W by the error rate divided by 1 minus the error rate. Okay, and finally, they normalize the weights, and then, so far these were all weights of data instances, but then we also need to compute a weight for the hypothesis, and we're simply going to take the log of 1 minus the error divided by the error. Okay, so now you might wonder, where do those expressions come from? So here, why do we multiply by error divided by 1 minus the error, and why do we take the log here? So there's some theory behind this. So when AdaBoost was first proposed, with these particular expressions, you can prove some bounds on the quality, the accuracy of the approach. And you can also prove that by using these specific expressions, you're going to necessarily improve in the long run the accuracy. Okay, so boosting works well as long as we have a weak learner. And here, a weak learner, it simply means an algorithm that produces hypotheses that are at least as good as a random classifier. So I guess the bar here is pretty low. Okay, so if we're doing binary classification, so a random classifier would just obtain 50% accuracy, right? And now we simply require it to be better than random. And now you might ask, well, what if it's worse than random? Then if it achieves accuracy lower than 50%, then what you could do is simply flip its label. So whenever it says true, just believe it's false. Whenever it says false, just believe it's true. And then you will essentially have an accuracy that's higher than 50%. So basically, you can pretty much always ensure that you have a classifier that is at least better than random, because if it's not, you just flip the labels, and then it will do better than random. Okay, so some examples of weak learners could include perceptrons that we've talked about. There's also decision stumps. These are really just decision trees with a single node. So a tiny, tiny, tiny decision tree of a single node. You can have some simple rules of thumb that are manually specified. You can also have a naive Bayes model. So we haven't covered some of these techniques, but these are just examples. And here, the idea is that in general, boosting is most effective when you work with simple, weak learners that perhaps are far from perfect. And you might say, well, why don't we just use some better deep neural networks? So as we discussed before, in some cases, it's not worth it. And the point is that we're going to generate a lot of those hypotheses, right? So you see, every iteration here, we're calling the base learner once. So now if you have a deep learning technique that takes days to train, right, then every iteration of this loop is days that you have to wait, right? So here, boosting, generally speaking, we would apply it with some weak learners, and also learners that are fast, so that we can iterate quickly over this. Okay, so some of the advantages of boosting is that now we don't need to strive for perfect hypothesis, because we're going to boost the weak learner. And then the boosting algorithm is itself very simple. So you see, if we look at this algorithm, I mean, this is a couple of lines, right? It fits on one slide. There's nothing complicated about it. It's beautiful. and then it applies to pretty much anything. Okay, the other nice thing is that boosting tends to be robust to overfitting, and that's in part because we have multiple hypotheses, right? We're not just picking one hypothesis. Like what would be tempting is just to pick the best hypothesis that we generated in the whole bunch, but no, we combine all of these hypotheses, and the danger of picking the best one is that the best one might really just be fitting noise in the data. So that's why you want to combine it with some of the other hypotheses that are not as good because they might actually generalize better. And overall, we can think of boosting as really being an approximation to Bayesian learning. Right? So when we generate multiple hypotheses with some weights and we take a weighted combination, this is similar to Bayesian learning where we have a posterior distribution over hypotheses, and then to make a prediction we also took a weighted combination. The difference is that here we have a specific way of generating the hypotheses, whereas in Bayesian learning we would simply consider the entire space of hypotheses. Right? So we can think of this as like a tractable approximation to Bayesian learning, where you just generate one hypothesis at a time. You're being selective, so you're not going to generate necessarily an intractable number of hypotheses, but you still get the nice benefit of good generalization because you're combining multiple hypotheses. Okay, so boosting is generally very good whenever we have a bunch of hypotheses that we also are looking for a principled way of combining them. So in engineering, for decades, people have talked about how we can do sensor fusion or combining experts, right? So there are all kinds of heuristics that have been proposed to do sensor fusion, but now this is a principled way of combining the predictions that would be made by different classifiers or different predictors, perhaps based on different sensors, and then ensuring that you're going to end up with good accuracy overall. A lot of the other heuristics might not come with any theory and they might not always work, whereas this is quite robust. Okay, so there's lots of applications for boosting. Perhaps one of them that became famous, and I'll tell you a bit more about the story, is regarding the Netflix challenge, where Netflix essentially was in a business of recommending movies, and is still in that business, right? So, and the idea is that there's an interesting question about finding movies that a viewer might be interested in, right? So there's a whole slew of movies out there, and after a while, there's a lot of movies that you don't find interesting, and you're really looking for good movies, right? So then Netflix, for a long time, has had an automated recommender system, and the idea is that they would like to essentially improve the accuracy of their recommender system, and then boosting and ensemble learning ended up being key for this. Another important industrial application is the Kinect produced by Microsoft. So if you've played with the Kinect over the years, at the beginning at least, the way they were doing the body part recognition was essentially by considering an ensemble of decision trees. Okay, so in general, any supervised learning task, you can use boosting or you can use some form of ensemble learning. And then even if you already have fairly good hypotheses, as long as they're not already perfect with respect to your training set, then there's a chance that you can combine several of them and obtain a little bit of a boost. Okay, so let me tell you a bit more about the Netflix challenge. So this was an important challenge that occurred many years ago. So it was launched in 2006, so that's more than 13 years ago. And in this challenge, Netflix was interested in improving the accuracy of its recommender system and essentially proposed a challenge where if anybody could improve the predictions that Netflix was already doing by 10%, then they were going to give $1 million. Now, this particular competition was quite a landmark because there had not been so many competitions before the Netflix challenge. And then this was a high-profile competition as well because of the $1 million. Now today, there are many competitions, and then Kaggle is now essentially organizing all of these competitions, but this is all before Kaggle even existed. Okay, and also having such a large prize was unheard of because back in 2006, AI and machine learning was not popular. There were just a few companies like Google, Netflix, and others that actually understood the power of machine learning. And already for Netflix, the fact that they were willing to provide $1 million meant that to them, improving the accuracy by 10% was actually worth even more than $1 million. Right? They were not just going to give out a prize for just being nice. Right? I mean, there was economics behind this, and there was value in improving the accuracy by 10%. Okay, so they launched the competition in 2006. The goal was to improve accuracy by 10%. After 1 year, the best team was called Belcore, and they achieved an improvement of 8.43%. Now, unfortunately, this did not meet the threshold of 10%, so they did not win the $1 million. Instead, the competition kept on going. And then after 2 years, in 2008, there were no individual algorithm, no individual team that managed to improve the accuracy by more than 9.43%. So there was some improvement with respect to the previous year, 8.43, but still was not reaching 10%. But then at that point, in year 2, the top 2 teams, according to the leaders board, decided to unite and work together. So they decided to use Ensemble Learning. So this was the first time that somebody in a competition thought about doing Ensemble Learning, and I guess here with high hopes. Okay, so then by joining together, so this was Belcore and Big Chaos, they had a tiny ensemble. They managed to get an improvement that got them past 9.43%, but still less than 10%. So it still wasn't good enough. Okay, so then in year 3, on June 26, the top 3 teams decided to unite. So Belcore, Big Chaos, Pragmatic, and then jointly they improved with their ensemble and passed the 10% mark. So according to the rules, then at that point, any other team who wanted to challenge them had 30 days to submit something better, something that could beat them. Okay, so now there was a countdown, and if no one else, then they would win. Okay, so at that point, the other teams realized, well, hey, if 3 teams can work together and form an ensemble, why can't we work together and also form an ensemble? And in fact, there were many teams, right? So we could form a bigger ensemble. And we know from boosting that you can boost those weak learners. So if you're a competitor and you don't have such a good solution, that's not a problem. We'll boost you, and then as part of the ensemble, you can contribute and obtain a good score. So here they proposed a new team. It was called the Grand Prize team. So the goal was clear, right? And anyone was invited to join. There were literally emails sent to all researchers out there. And then the scheme was as follows. So if you join, you would share $1 million of the grand prize proportional to the improvement in the team score that your algorithm contributes. Okay, so let's say the accuracy is already at 9.2%, and now you manage to improve it to 9.3%, so that means 0.1%. You're going to get 0.1% of the $1 million. Okay, so several teams ended up joining like this, even if that meant maybe some small amounts, but they managed to get to 9.46% like this by forming this grand prize team. So then at that point, 5 days before the deadline, there was an even larger ensemble that got formed, and it was the union of the grand prize team with Vanderlei Industries. So this was a company participating. And then that created an ensemble of many researchers. And then on the last day, July 26, 2009, then at 6:18 p.m., Bell Course Pragmatic Chaos submitted their final solution, 10.06 improvement. This was on a test set, okay? So they submitted the solution, it got evaluated. This was the result on a test set. And then at 6:38 p.m., the ensemble team also submitted its solution and matched this at 10.06%. So then the winner was essentially determined by the time of submission. So Bell Course Pragmatic Chaos won the $1 million. But okay, through this competition, people understood now the value of ensemble learning. That was the key to win in this challenge, right? There was not much improvement after the first year, and then really the improvements after that were through ensemble learning. So now when you participate in a competition, don't be surprised if you see a lot of teams that are essentially creating ensembles, not necessarily with other teams, but just within their own team, they're going to form ensembles of hypotheses. And the idea is that you can boost perhaps your accuracy by a few percentage points. So usually with ensemble learning, if you don't start with weak learners, but if you start with already fairly good solutions, then you can obtain a boost. It's not going to be a very large boost, but still if you get 1 or 2 more % accuracy in some competitions, that might be the key for winning, right? So yeah, so that's the story, and then that's how since then, in pretty much any competition, you will see people using ensemble learning. Any questions regarding this? Yeah.
Sorry, I think all of the teams just participating in this ensemble have strong learners, not weak learners. I mean, each of the models are just can behave very well individually. And I'm just wondering how it works. None of them are weak learners.
So so you're talking about this team here or that team here?
Actually, no difference, because anyone who wants to, who has participated in this competition, just did his best to win the prize. So most probably they have just provided strong learners, not weak learners. So ensembling strong learners also have a good.
Yeah, okay, good point. So yeah, so here everybody who participated obviously was trying to win, therefore was producing strong learners. But okay, this was before the deep learning era, and those strong learners were still limited, and there was clear benefit in combining them. Now today as well, still, even with deep learning, you will see, like for instance, in the ImageNet challenge at the beginning, in the first few years before accuracy really overpassed human performance, then people used to submit as well little ensembles of maybe 5 to 10 neural networks as well. So yeah, so generally speaking, it helps. If you're not already, at the limit of what is possible given the data set, then you can still obtain a boost. That boost is not going to be very large. I mean, you can see they were already, like, for one team at 8.43, and then to get this additional 1.57%, right, then boosting was needed. Yeah.
How did they handle the computational overhead? Like, imagine from place 4 to 10 in the standings, they weren't really weak learners. Like, these were sufficiently complex models that took some time to train. If you combine all of them and all the hundreds below or however many, that seems like infeasible competition.
Well, okay, so I guess with boosting or ensemble learning, the combination can be achieved through distributed computing because you can have every single hypothesis that runs on a different machine or uses a different core, right? And so it's not that much of an overhead from that perspective. Now, if you're talking about what about in production, would Netflix use this? I don't know. I don't know what they ended up doing. But then, yeah, so I guess at scale, these things would matter. And in the industry, ensemble learning has this disadvantage that you will necessarily incur a higher cost because you have to produce all of these hypotheses. And so there's obviously a preference for not necessarily doing that. Yeah.
Slide 13. So we're taking the weighted combination of the outputs of the hypothesis, right? We're not taking the weighted combination of the weights to get one hypothesis.
Okay, so slide 13. So yeah, here we take the weighted combination of the predictions, not the hypotheses. Yeah, yeah. So just of the predictions.
So we still keep all these hypotheses like separately sometimes.
Yeah, we keep them all separate, and then we take a weighted combination of the predictions. Now, in fact, it's tempting to just take a weighted combination of the hypotheses themselves. So we're going to discuss this in another lecture next week. So there are potential pitfalls with that because you might have two hypotheses, and then when you take their average, you get something in between that is worse. So that might not always work. Yeah.
Just to follow up, switch to the next slide.
Yeah.
So the weights end up being that very last line. So set M.
Mm-hmm.
You just do a little bit of computation on the error, and then at the end you normalize that, like, and return a weighted. The predictions of each hypothesis weighted by that.
That's right. So yeah. So here, there's a simple calculation that gives us a weight, and then when I say here weighted majority, the idea is that every hypothesis will make a prediction, and now we're going to combine those predictions, not the hypotheses, just the predictions according to those weights here. And then yes, we should. I believe the weights would get normalized. It depends if we're doing classification or regression here.